Good morning. Yesterday, I posted a video of some examples of related rate problems in context, and I gave you 4 problems for an assignment. I'm actually in this video going to do those 4 problems and then assign, I think it's 4 more. And I'll do that again tomorrow, go over those and assign 4 or 5 more. So again, the more different contexts you see, you have to get comfortable with different contexts doing this process. And the process here is identifying what quantities and rates are given and asked for, coming up with the correct equation that you need to use that relates all those variables, taking the derivative with respect to time, using the implicit differentiation and the chain rule, and then substituting in all the given information, excuse me, to solve for whatever. So here we go. 11 says the radius r of a circle is increasing at a rate of 4 centimeters per minute. Find the rates of change of the area when r equals 8 and r equals 32. So let's, again, we have to be able to, what am I doing here? We have to be able to identify what they're telling us. The radius is increasing at a rate of 4 centimeters per second. That is the rate of change of r. So that is dr dt. It's telling us that is 4. And question A says find the rate of change of the area. So that's dA dt. And for question A, it says when r equals 8. And for B, it says when r equals 32. Well, both of those have to do the same equation. So once we take the derivative of the equation, we can use that same derivative for both parts A and part B here. So I need a formula that relates the area of a circle and the radius. Well, we know that one. That's just area equals pi r squared. So that's the formula, the equation that we're going to take the derivative of with respect to time. So the derivative of A with respect to time is dA dt. And the derivative of pi r squared is 2 pi r dr dt. And now it's just a matter of substituting in what we know. We know that dr dt is 4. Question A said when r was 8. That's a pi and that's a 2. Not sure I wrote that backwards. That turns out to be, what, 64 pi, I believe it is. So it'd be 64 pi, and again, let's be comfortable with the units. This is area with respect to time. So that is centimeters squared in this case. And it happens to be per minute. And then part B, again, I'm gonna, because it's the same equation, same context, this right here, I can use again. I don't have to start all the way back from the equation. Part B said when r equals 32. So in this case, it is dA dt equals 2 times pi times r is here 32. And it still gave us dr dt was 4. And that is, let's see, 8 times 32. It's at 256 pi. 256 pi, and it's still centimeters squared per minute. So, and we can see one earlier where we had used the formula for the area of a circle. It is one of the basic applications of it. So there's number 11. 14. A spherical balloon is inflated with gas at the rate of 800 cubic centimeters per minute. Stop there. That's telling us how fast air is being pumped in, and that's changing the volume of the balloon, how much air. It's a 3-dimensional quantity, volume. So this problem is telling us that dV dt equals 800. And it says, how fast is the radius increasing? So find the radius, find dr dt. And then it gives us 2 problems. A, when r equals 30, and B, when r equals 60. So there, again, we want to clearly identify what rates or quantities they're giving us and what rate or quantity they are asking for. Now I need an equation. We're talking about the volume of a sphere. We saw this from yesterday also. The volume of a sphere is, in fact, or the formula for the volume of a sphere is 4/3 pi r cubed. So that's the equation we take the derivative of with respect to time. So I have dV dt And the derivative of 4/3 pi r cubed. Remember 4/3 and pi is just a constant. Bring the 3 out front. I end up with 4 pi r squared dr dt. And now it's just a matter of for A and B plugging in what I know. So let's see, for part A, dv dt they gave us, so it's 800, equals 4 times pi times r squared. R for part A is 30. And then dr dt is what we're trying to solve for. That becomes 800. 300 squared is 30 squared is 900 times 4 is 3600 pi dr dt. And then we saw one of these yesterday. Let's be really careful with how we finish this. If I divide by 3600 pi, I get 800 over 3600 pi. Just make sure you're clear that in this case, the pi is still in the denominator. That's dr dt. Now, extended response question, welcome to end there. If it made you make decimals, you could. If I would just reduce this, I see zeros that can go away. Now I have 8 over 36. I can divide both those by 4, I think. I end up with 2 over 9 pi. Again, the pi is still in the denominator. And this is now the rate of change of the radius, which is a one-dimensional, so that would be centimeters per minute in this case, I believe. And then for part B, the only difference is we're plugging in a different R. So it's still 800. It's still 4 times pi. Instead of 30 squared, it's 60 squared times dr dt. That becomes 800. 36, that turns out to be what, 14? I did this earlier. 14, yeah, 14,400. 14,400 pi dr dt. So my answer becomes 800 over 14,400 pi, which again happens to reduce to 1 over 18. So it's 1 over 18 pi, and that is still centimeters per minute. So we had question 11 was the area of a circle. Question 14 was the volume of a sphere. And then 15 and 16 both have to do with a cube. 15 says all edges of a cube are expanding. And I draw, well, it's a cube. So all these dimensions are all the same. There went my lights. All these dimensions are the same. They're all x, since it's a cube. That's nice. And it says the edges are expanding at a rate of 6 centimeters per second. That's how fast that quantity x is increasing, how fast it's changing. So dx dt equals 6. This problem tells us that. How fast is the volume changing? So it wants us to find dv dt. And again, we have two different, when each edge, when x equals 2, and then part B is when x equals 10. So I need a formula for the volume of a cube. Well, a box, the volume is length times width times height. And of course, here that's x times x times x. So the volume of a cube is just x to the third. There's my equation. Take the derivative of that with respect to time. I get dv dt equals 3x squared dx dt. And now it's just for part A and part B, just plugging in the right value of x and dx dt. So we'll do part A in blue. That's an A. So dv dt equals 3 times x squared. For part A, x is 2. And dx dt, the problem told me it was 6. That is 4, 12, what, 72 maybe? 72. And again, this is dv dt. So it's a unit for volume over a unit for time. So in this case, that is centimeters cubed per second. And then for part B in purple here, the only difference is my value for x is now 10. So dv dt is 3 times 10 squared times 6. That's a 2, which is what, 1800 maybe? 1800 still centimeters cubed per second. That would be dV dt. So number 15 had to do with the volume of a sphere. All right, last one is 16. The first sentence is the same. We still have a cube, still x by x by x, and it's still telling us that the edges are increasing at a rate of 6 centimeters per second. That hasn't changed. Now this says, how fast is the surface area changing? The surface area is the area of all of the faces. Well, there are 6 faces on a cube. Each one of those faces is a square that's x by x. So the area of one square would be x squared, and there are 6 of those. So the surface area turns out to, the formula for the surface area is 6x squared. Let's take the derivative of that. And I'm going to write this as dSA dt. A little awkward, but nothing wrong with that. The derivative of 6x squared with respect to time is what? 12x dx dt. And now let's just, again, as always, substitute what we know here. So for part A, dSA dt equals 12 times x. And for part A, x is 2 and dx dt is 6. What's that, 144 maybe? That's 144. Now it's the rate of change of area with respect to time. To get your units correct here. So that in this case would be centimeters squared per second. And then for part B, the only difference is a different value for x. So dSA dt equals 12 times 10 times 6, which is what, 720 maybe? 720 centimeters squared per second. So there is your explanation of the 4 problems from yesterday. And tonight's homework is several more. And we are doing, I lost it, during just 17 and 18 and 21. And I will tell you that 21 is essentially 3 problems because it has an A and a B and a C. And in this case, all 3 of those are different equations you have to use. It's the same context. It's kind of a classic context of a ladder up against a wall. So it's essentially 5 problems. Again, the more exposure you have to different contexts, the better off you will be. So that is it for today's video. And I will, again, post the solutions to these tomorrow and then give you, I think, one last set then. So have a great Wednesday. It's Wednesday.